4 technical universities are on a mission. Students and professors are studying, working, contributing to make the energy transition possible. This is their story.
So here at TU Delft, we're studying the behaviour of the subsurface and its ability to provide us heat that we can use directly for our buildings. Our existing buildings need high temperature heating to supply their energy demands. We can get this ideally from geothermal energy, which can supply those temperatures directly. This allows us to have the energy transition fast, with having relatively limited renovations in our buildings. At the heart of what we're doing here on the campus is a deep geothermal well. And what we're doing here is having a well that will produce heat that will be used to heat our buildings and areas beyond the university, but also that we can study in detail to understand exactly how it behaves. We can take samples from this large project into our laboratory and we can look at the small scales of how they behave, how the water flows through the sample, for example, and we can understand from our large-scale measurements how this impacts the larger projects. This knowledge will really help us upscale the technology so the whole country can benefit from geothermal energy. In the years to come, we will also install an energy storage system. This allows us to produce heat during the summer, when we don't need the heat, store it in the shallow subsurface, and reproduce that heat in the winter. This means we can cover more of our energy demand with sustainable heat. The overall energy system needs different storage and different materials throughout, and this is where we can also collaborate with our 4TU partners.
My research focus is on salt, and it sounds strange, but we can use salt to store energy. And the way it works is basically as follows. Salt can absorb water into the crystal structure, and then heat is released. And you can reverse that. So if you have heat available, you can bring it to the salt, you drive out the water, and in that way you charge the salt. Now what you see here is a salt powder. As a powder we cannot use it in a heat battery, so we really have to manufacture particles out of that. Now, if you're going to discharge and charge your heat battery, you want to do this several times, let's say 10 or 100, maybe even 1,000 times. So therefore these particles should be stable. So one aspect of the research here is to stabilize these particles. The second aspect is that you want to bring in the heat in and out very fast. We try to find dopants, additives, which facilitate the reaction, accelerate the reaction. And in this way we can improve the power output of the material. My vision as a physicist is that I should go beyond, let's say, physics and engineering. I should also have a look at materials development on societal impact. If you select a salt, you have to keep in mind that it will be used in large quantities. So it should be mined in large quantities, it should be produced in large quantities. And at the end of the life of your heat batteries, there will be a large amount of salt available. So in all these steps, you want to make sure that your system is sustainable. And that's where you can select your materials on. And we with the heat batteries are not the only ones working on devices for the energy transition. So our materials should not be in competition for resources with other applications. Think, for example, on electrical batteries. There, lithium is a key ingredient.
Heating is an essential part of our daily life, which is dominated by fossil fuel, causing a lot of CO2 emissions. Here at University of Twente, our mission is to achieve 100% sustainable heat. And for that, heat storage is a key. We are working on PCM and TCM-based heat storage systems. In the first case, in case of PCM, we are taking advantage of solid to liquid phase change, and in case of TCM, we benefit from the solid gas reactions. To realize a reliable performance, we need to have stable materials and systems. And that's why we are equipped with different material characterization facilities to look on how our material is performing and how, for example, the structure of the material is changing over the lifetime of the device. Furthermore, we have developed an advanced numerical platform which is capable of revealing very detailed information on different scales, starting from the particles to the patch bed reactors. With these combined numerical technologies and experimental facilities we are capable of looking on how our material and systems are performing and how they can be improved. I strongly believe that energy transition cannot happen without introducing heat storage technology. For that, we need to team up with different skills and different expertise. So far we have been focused mainly on the built environment, but I do see the potential for the industrial waste heat recovery and also for the district heating.